All right, now we've talked about the relationship between linear operators or linear mappings and matrices. So just keep in mind that everything we talk about matrices is also going to apply to linear operators. And linear operators are very useful in many areas of study. All right, that will all unfold as we continue to talk about these things. All right, so let's go to some definitions. And we've seen some of these things before, but we're going to express them in general component notation. If we have a R by K matrix, it can be represented in this way. The superscript refers to the row, and the subscript refers to the column. R by K means R rows, K columns. All right. If we have a R by 1 matrix, that's called a column vector. So that means R columns, R rows, 1 column. Right. So VR1, so the subscript is 1, so you can just ignore the subscript and just look at the superscript, which is the row index. On the other hand, a row vector is a V1K, so we don't need to write the superscript. We can just write the subscript, and the subscript tells us which entry. Now the transpose of a column vector is a row vector and vice versa. And this transformation expressed by transpose is called an involution because it is its own inverse. If you take V transpose transpose and you get V back again. And that's either whether V is a row vector or V is a column vector. Now matrices can be used to store information. For instance, graphic information. Now a picture can be thought of as a plane. At each point on the plane you have a pixel, and of course the location in the plane is specified both by the row and by the column. So that corresponds to a matrix. Now in graphs, you also can represent the contents of a graph by a matrix. Now graph in mathematics doesn't just mean the graph of y equals x squared, something like that, but graph means structure consisting of nodes or points connected by edges. So here we have a structure where we have 4 nodes, 4 points connected by several edges, and here we say that if 1 is connected to 2, then 2 is also connected to 1. That's called an undirected graph. In some cases you have directed graphs, but here, since there are no arrows on the connection, this connection indicates that 1 and 2 are connected. Now in fact 1 and 2 have 2 different connections. So in the matrix entry labeled by 1 and 2, you're going to have the number 2. Right. So the formal specification of the matrix associated with this graph is Mij, where Mij is the number of edges from I to j. So for instance, M12 would be 2 because there are 2 edges from 1 to 2. And M21, as we mentioned, also has 2 edges. So you can see that M12, row and column 2, that's here. M21, row 2, column 1 is here. They're the same number. So this matrix is called a symmetric. If you draw a line down the diagonal and you look above and you look below, you'll see the same thing. Here's a movie that talks more about adjacency matrix. Right, so formally we can specify this set of matrices. Here this just means I is in this set of row indices, j is in this set of column indices, and each entry in the matrix is a real number. Now matrices satisfy these linearity properties. There has an addition, you have a scalar multiplication. So in fact you can run through all the vector space axioms. And as we've mentioned previously, this set of matrices is a vector space. In a special case, if we have a matrix with just 1 column, that's the column vector space which we've seen before. Now, multiplying matrices, the way you think of multiplying matrices is you multiply the first matrix times each column of the second matrix. Now we saw this matrix column vector multiplication rule before. Right? So that's what we have here. We have our matrix M, we have our matrix N. This is the specification of N, and N has columns like this, right? Column 1 has subscript 1, column 2 has subscript 2, and so on. So if I want to take the matrix M multiplied by the matrix N, I write M, and then I think of the N columns, of the S columns of matrix N broken out. And the product is also going to have S columns, and each column of the product is M times the corresponding product of N. Right? And we can write this in summation notation in a very concise way. Notice that this subscript P and the superscript P are the same. This P is called a dummy index because on the left-hand side the P doesn't appear, because this summation means the P is a varying index and has no set value, but after you've run over the entire sum, that gives you a result, Lij. Now, in order to multiply two matrices, they have to be of compatible size. The reason is that this subscript index P is the same as this superscript index P. So this subscript P is the column index of M. This superscript P is the row index of N. So it turns out the number of columns in the first matrix must be equal to the number of rows in the second matrix. All right. So there's a good rule. R times K means if you have a matrix with R rows and K columns, multiplied by a matrix with K rows and M columns, you're going to end up with a matrix that's R rows and M columns. So you basically cancel, the K's have to match, and you take the first and the last. First entry here is to get the row size, and last entry here is to get the column size of the product. And here are some examples. So this 3 by 1, this is 1 by 2, so you get a 3 by 2. Right. Now, the other way to see this is that every entry in the product is a dot product, and you're taking the dot product of the rows of M with the columns of N. How does that work out in this case? In this case, each row has only one entry. So for instance here, this 1 times 2, that's the row of this matrix times the column of this matrix. Okay. Be careful, there's a tendency to want to put the longer matrices on the left and the longer row matrices on the left and the column matrices on the right, but that's not necessarily true. If I write a column on the left and a row on the right, I'm going to get a different result from writing the row on the left and on the column on the right. For instance, if I wrote 2, 3 times 1, 3, 2, if I took the matrix, the vector 2, 3 first, multiplied by the matrix 1, 3, 2, that's not defined because the number of columns of 2, 3 is not equal to the number of rows of 1, 3, 2. So if I reverse the order of these two matrices, the multiplication is incompatible. But in this case, the multiplication is compatible because the 1 here matches the 1 here. Okay, so there's some more examples here. Here we have the definition of orthogonal. If we have a matrix M and a column vector X, then Mx equals 0. Then X is orthogonal to the rows of M. The set of possible outputs when you multiply a matrix times a vector is called the column space, which is a vector space. We can also define the row space of a matrix, which is the span or the set of all linear combinations of rows of the matrix. All right, in this case, if Mx equals 0, that means that X is orthogonal to every entry in the row space, so we could say X is actually orthogonal to the row space of M. Now, we know that matrices themselves form a vector space, and you can multiply matrices by a matrix. So a matrix acting on a vector space of matrices gives me a linear transformation. That's expressed in this equation here. The linear transformation L is the transformation affected by the matrix capital N from the vector space MSK. This is a vector space with S rows and K columns. And this is a vector space with r rows and k columns. And I get from the matrix here to the matrix here by multiplying by the matrix n. Okay? So L of m equals nm is a linear transformation. Just like we saw before that L of v equals nv is a linear transformation, I can replace the column vector v with the whole matrix m, and I still get a linear transformation. Okay. We know what a square matrix is. We know diagonal matrix is a matrix that has ones except on the diagonal entries. We know what the identity matrix is. It has all ones on the diagonal. The identity matrix times any matrix is that matrix. We know what the transpose of a matrix is. The ij entry of the transpose, well, I can say here the ij entry of the transpose is equal to the ji entry of the original matrix. And the matrix is symmetric if it's equal to its own transpose. Some examples of transposes. And it turns out that the transpose of the product is equal to the product of the transposes in reverse order. And we'll see that. And that's it for this recording.